Yeah, thank you very much for the introduction, Andy. That was very good. And I guess just to put this in perspective, I think the bulletin was conceived probably in about 2017. I'm not quite sure if that was when, but about there. And we struggled a bit as to just what the bulletin was going to be about. And in Ottawa in 2019, I think we made a huge step in really focusing on what elements we wanted to communicate in the bulletin. And the general philosophy of the bulletin is to take all of the components that are so important for tailing facilities, and we all recognize that they're very complex projects, and they go on for a long time. And so you have to always be looking at what's happening, what's going to happen. And the guidance that we have put together, hopefully it'll help people with respect to understanding just the different nuances and different components of tailing facility safety. And so this video will communicate the main parts of the bulletin, and we look forward to its adoption. Thank you very much, Andy, and thank you very much, particularly to the writing team. It's been 2 to 3 years of a lot of work, a lot of conference calls, and like with any committee, we have to agree on things. And so that takes time and effort. And I appreciate the patience and the persistence of all of our members on the writing committee. Thank you. The workshop, Tailings Dam Safety with Committee L, Tailing Dams and Waste Lagoons. And just for a matter of logistics, if you have questions during the presentation, please enter them into the chat box and we'll do our best to answer the questions. If there are some very urgent matters you wish to discuss or cover, then you can raise your hand, and if we have time, we'll allow time to speak. But we encourage you to put your messages into the chat box, and we'll try to respond accordingly. Now we have quite a bit of content with the bulletin, and obviously we can't present everything in the bulletin. We'll present what we believe are some of the important components of it. In some technical areas, we'll have more discussion. So our committee, we have a small working group, myself, Harvey McLeod from Canada, Annika Belkovic from Sweden, Raphael Monroy from the UK, Paul Ridlin, the United States, Duncan Grant Stewart, South Africa, David Brett, Australia, Thierry Hirza, Czech Republic, Joaquim Pimenta Davila from Brazil, and Andy Small, Canada. We also have Imran Jalani, who is a co-opted member of the International Council of Mining and Metals. He's co-opted for this particular bulletin to get some of the industry input. Now, a lot has happened in the last 4 years. I think we started our bulletin about 4 years ago. And since then, there have been several failures in Brazil. The Global International Standard for Tailings Management was released last year, and it's been adopted by the major mining companies. And there has been progress on the ICMM have developed conformance protocols for the standard. They've also developed a good practice guide for tailings management. And those bulletins or guidelines are primarily aimed at the operators and on the governance aspects with some engineering aspects. And the ICOLD Tailings Dam Safety Bulletin, it is aligned with the standard and with other guidelines, but it's focusing on the technical aspects of tailing dam safety. Now there's 12 chapters, and I won't read them all out, you can see them, and we'll cover components of each of these chapters in our talk today. We also have several appendices, and these are focused on the strength behavior, particularly understanding the strength behavior of tailings, because many of the upstream dams are potentially liquefiable materials, and understanding the strength and the behavior and how we apply them is critical. On the governance aspect, and apologize for the graphic there is hard to see, but key elements there are the roles and responsibilities of people. And this came out of the Mount Poly failure, where in our interviews with all of the mining people and consultants and everybody involved with the project, everybody was basically pointing fingers in every other direction because there was not clear distinction of responsibility. And we introduced the responsible owner, and now it's called accountable executive. The responsible person at the mine, now called a responsible tailings facility engineer, and the engineer of record and independent reviewers. The other component, and this is where ICMM has in their bulletin give very good guidance, is on tailings management system. It's important to have the systems in for tailings management. And the importance of risk assessments and reviews and audits, you can't overemphasize that it's always a benefit to have other people looking at what you're doing and to continue to improve and reduce risk. Other important components of governance is the incident and change management. Tailing dams are built over a long life, and there's construction going on every year, typically. And things can change, whether it's change in operations or changes in the understanding of the physical or environmental setting that you're in. And lastly, the documentation. It's critical to have documentation, particularly with these structures, because they're built, as I mentioned, over such a long time, data that can be lost. And it's important to be documenting all the geotechnical data consistently throughout the life of the facility. Now, we made the first technical chapter in the bulletin on closure because, in essence, we're designing all of our facilities for safe closure. We use the mine for a number of years, and then we close the mine, and we want tailing facilities that are safe. The ICOLD Bulletin 153 gives good guidance on sustainable design of tailing facilities with the objective of returning it to a sustainable land use. So we have the physical, geochemical, ecological, and social stability, our main components of a safe dam, with the ultimate goal of reducing our risk to basically negligible to non-credible. The bulletin also outlines loading design conditions for closure, as well as sustainable design considerations. So we encourage you to go to that bulletin to get further details.
This next set of slides is on Chapter 4, the Dam Consequence Classification. We received several comments on the Dam Consequence Classification chapter, and we felt it was appropriate to provide you with the update that we currently have in the bulletin on Dam Consequence Classification. There are various classification schemes in the world related to size and hazards as presented by the dams, and ICOLD, CDA, and others have classification schemes based on consequences of failure. At ICOLD, we felt that that was the appropriate approach for classifying a dam based on the consequences of failure with respect to population, environment, societal, and economic impacts. The classification framework that we're going to be presenting to you today is similar to that proposed by the Global Industry Standard on Tailings Management. The Dam Consequence Classification is used to inform the dam safety stewardship and management programs, provide transparency to external stakeholders on the outcome of a dam failure, to meet a regulatory or stakeholder requirement, to support a comparison of TSFs in different regions and jurisdictions. Dam Consequence Classification is used to inform the selection of design loading criteria. The design criteria that are based on dam consequence classification is typically considered as a minimum. Other factors need to be considered when establishing the design criteria, such as the potential impacts to the owner and the potential risks to life safety. When classifying a dam, we assume that a failure mode may occur that is physically possible as a technical basis for occurrence. This has to be a very rigorous undertaking to demonstrate which failure mode you're considering. And the dam consequence classification is supported by an estimated runout or inundation. That does not necessarily mean a detailed runout or inundation study. It could be simplified as well. A confusion that we often run into is that consequence classification is used interchangeably with risk. That is not the case. We're just focusing on the consequences here. We're not addressing the likelihood in the consequence classification, and therefore the consequence classification should not be considered as a measure of risk because likelihood is not taken into account. We recommend that the dam consequence classification be done for two conditions: the sunny day or fair weather failure condition, and the flood failure or wet weather failure condition. Often, the dam consequence classification is initially assessed qualitatively with a simplified approach. More detailed dam breach analysis and inundation may be required for high consequence classification dams and above. The dam consequence classification that is developed needs to be considered as an indicator and still need professional judgment to arrive at the consequence classification. And obviously, the dam consequence classification scheme does not replace what's required by regulation. So this slide shows the classifications framework that we have developed at ICOLD. On the left-hand side of the table are the dam failure consequence classification, ranging from low to extreme. Across the top of the table are the different categories: population at risk, potential loss of life, environment, health, social, cultural, and infrastructure and economics. If you were to compare this to the GISTM consequence classification scheme, you'll find that it's quite similar. However, we have removed many of the numeric values. For example, under the infrastructure and economic losses, you will not notice reference to dollars. In the GISTM and in the previous version of the ICOLD bulletin, we had different dollar thresholds there. But what we have been advised is that a moderate economic loss in one jurisdiction may not be a moderate economic loss in another. Under the environmental column, we've used the term environmental values, and we've defined those. We've removed the released contents chemistry aspects. In the GISTM, there was discussion about whether the tailings are acid generating or metal leaching, and those are important considerations, but they are embedded within the environmental values discussion. So just to focus in on the high consequence classification, population at risk between 10 and 100, potential loss of life between 1 and 10. Under environment, a significant loss or deterioration of critical environmental values, and we define those. Potential contamination of livestock, fauna, water supply. We're often asked, well, what about human water supply? Well, that is picked up under health, social, and cultural, as well as infrastructure and economics, in terms of providing replacement water supplies. The potential area of impact between 5 and 20 square kilometers, and restoration possible within a moderate time frame. And what does moderate mean? Well, again, that becomes jurisdiction specific. In some cases, restoration can occur within a few years and be quite satisfactory. In other cases, it may take longer to get there, but that still may be considered as a moderate time frame. Under health, social, and cultural, many people could be affected by disruption of business, services, or social dislocation, significant loss of regional heritage, recreation, community, or cultural assets, and there could be some short-term human health effects. Under infrastructure and economics, high economic losses affecting infrastructure, public transportation, and commercial facilities or employment, with moderate relocation compensation to communities. There can be a misperception in industry that by designing a dam for high consequences, that is potentially 1 to 10 lives lost, then if the dam were to fail under conditions that were larger than what the design criteria had been adopted, then it would be somehow acceptable to have more than 10 fatalities. That was not the intent of the dam consequence classification framework. A key purpose of the dam consequence classification framework was to provide a rational, objective, and transparent framework for classifying a dam. So when you say to someone that the dam is classified as significant, that's understood. That means something. Or if you say the dam is classified as very high, that means something. When it comes to establishing the design criteria for the dam, and we said this earlier, the owner needs to decide on that design criteria that considers potential risk to life safety. As indicated by the ICOM guidance, extreme loading conditions are being recommended for dams with even one potential loss of life, and several mining companies are adopting that approach. Many of you are familiar with the concept of credible failure modes that was introduced by the GISTM in 2020. In 2021, ICMM provided further definition to the credible failure mode concept, but there's still not a consensus in our industry on how to define these. From ICOLD's perspective, where we focus on the design and safety assessment, we did not address credible failure modes. You will note that in doing the dam classification, we're asking that you focus on failure modes that are physically possible and have a technical basis for occurrence. Now, we do recognize that for emergency planning, this may not be appropriate, and that the failure modes for emergency planning should consider likelihood. This last slide on Chapter 4 indicates that the classification can change over time with changes to the TSF and external environment. That the consequence classification, again in combination with potential losses to the owner, should guide the investigation, design, construction, operation, and closure.
Our next speaker is Jerry Herzog.
So we're just going to take a pause here for a moment because that's a very important chapter that we just went through. And wondered if anybody had any questions or comments on what they've just seen here. Oyvind is helping us with the technical aspects today, and he has a microphone. If you have questions in the audience here, please put up your hand. And Oyvind, I lost that chat you had pulled up for me. And then we have one comment in the chat that Oyvind has on his phone. I've just got to get it back. So first, for those in the room, does anybody have any comments or questions here? Paul and Jerry, would you like to add any other color to the discussions we've been having?
If I may, excuse me.
It sounds like Jorge.
Jorge Troncoso from Chile, coming back from the cold. Two questions about the engineer of record role. We in Chile have the feeling that the engineer of record should be an independent individual with all the high qualification that you have properly input in the bulletin. But the one sentence we object is the one that says that in some cases, the engineer of record may be an employee of the owner and so on. We believe that sentence should be eliminated or worded differently because we don't want it to open the door for, just a subordinate. So if the engineer of record is a subordinate of the owner, the communities and in general outside are going to decrease the value they have in the opinion of the engineer of record. The engineer of record is supposed to be, in that case, will be under high pressure from the owner. Yeah? And maybe that may cause some problems. And the other thing is that we should also indicate that the job of the position of the services of the engineer of record should not be chosen by licitation with money. I think this is a risk in that case that because of the licitation, people will try to win by lowering the price, and that will start with a very limited capacity to actually perform the work. Finally, we believe that the engineer of record should be in direct contact and very frequent contact with the owner or the representatives. And there is a sentence there that should report once a year. And according with our experience of engineer of record, we believe that reports of the engineer of record should be much more frequent, probably at least once every quarter of a year.
Okay, Jorge, it's Andy here. Thank you for your comments. We are unable to remove that statement about the internal employee, but I do recognize your concerns and maybe we can elaborate more into the conditions with which that's satisfactory. In terms of the reporting of the EOR, that's something maybe I'll pick up with you separate. I think you're aware that I chair a separate working group within USSD and CDA on engineer of record, and your point is very important there, but I think that's maybe a bit beyond the scope of the bulletin. Does anybody else here have a question or comment, Elias, in the room here?
Good morning.
Introduce yourself first, please.
Yes, Elias Batista from Mozambican Commission on Dams. I'm working for a mining company in Mozambique, Vale. Some of the important information regarding the new bulletin and the application and this use of GSTM called for some requirements regarding how we can consider the reputation on the classification of the dam. Some of the tailings management systems use reputation as one of the criteria to classify the dams, but it's something not usual in the industry. But I think it's something that we need to address, how we can address this on our classifications to it will be more restricted, but it somehow can have some contributions regarding how the community and how the stakeholders engaged can see the importance of a dam in a certain area. Thank you.
Yeah, the dam classification is intended to provide an objective indication of the potential consequences to society and environment. The dam classification is not intended to talk about owners' losses and owners' considerations, and reputational impact is an owner's issue. Every owner has their own scheme with which they determine the reputational threshold that causes them concern. So no, we don't wish to include things such as reputational impact, and it's too subjective and too owner specific. I think Suzanne had a question, and then I have one on the chat. Suzanne, go ahead.
Suzanne Lacasse from Norway and I guess Canada too.
Yes.
My question is, it's not particular tailings dam. We have the same problem with the water retaining dam. And you have this classification based on consequences, which will, you said it will direct the site investigation, like all actions to be done. Now, if you have two dams with the same consequence, but they have different hazards. One might have a failure probability 10 to the -1 per year. The other one might have 10 to the -6. This is what's too extreme. And then these two dams require different actions, or I guess this would not apply exactly during design, but during the lifetime of the tailings dam. And at least for water retaining dam, we find it more and more difficult to just look at consequences.
Absolutely.
Because you have to decide where you use your resources best.
Yeah, absolutely.
And the dam with the failure probability 10 to the -6 and the high consequence classes maybe should not be attended to before the other one.
No doubt about that.
So
We're not talking about prioritization. We're talking about informing and guiding. It needs to be coupled with the risk assessment, as you say, to actually establish a prioritization. The risk assessment is essential to this exercise as well. Thank you, Suzanne. And then within the chat, the question was asked, under the consequence classification, a potential loss of life of none, does this indicate potential loss of life of 0, or is 0.1 included? I ask, as the PAR is 1 to 10, this could be misinterpreted unless clearly defined. I think that's an interesting perspective. So it's intended to be 0 is what we intended there, not 0.1. So we'll just pick up on that and make sure that's clear. Okay, so we're going to continue now. I'm just going to go back to my desk to hit play. Maybe I can do it here. And then These next two sections were done by Jerry on site characterization and tailings characterization. After the two section size.
And there were two questions in the chat.
Oh, I see. My apologies. Didn't scroll down. The terms negligible and non-credible risks specifically defined. The answer is no. I addressed that, and that we stayed away from the term credible in this bulletin. After sections 5 and 6, which are Jerry's sections, we'll pause again for an opportunity for questions related to site characterization, tailings characterization.
And he's going to cover site characterization and tailings characterization. Jerry, I'll turn it over to you.
The objectives of site characterization is to understand and define the parameters and characteristics of the TSF site that might be impacted by the TSF or that might impact the TSF design, construction, operation, and closure. It covers not only the dam site itself, but the tailings storage area, as well as the potential dam break impact zone, and tailings themselves, as well as any other important structures. The objectives of next slide, yeah. To achieve those objectives, we describe an iterative process of studies and investigations to gradually improve our understanding of the TSF site from many different perspectives. Social environmental setting, geomorphology, climate, hydrogeology, seismicity, and most importantly, for the integrity of the dam, the geological and geotechnical conditions, which I will talk about a little bit more. Next slide, please. The outcomes of the site characterization, which is basically a process of integration of knowledge, are ground models. The ground models are models that describe a specific setting of the TSF site from geological, hydrogeological, or other perspectives. The ground models, and the next slide, Avi, the ground model captures the factual conditions and information for the respective objective of the model. It might be a geological model that captures the setting. The ground model is then used to define design models, which capture interpreted conditions to be used in specific design for specific design purposes. For example, for assessment of seepage or assessment of seismic induced deformation of the embankment. And finally, the design model is then transformed into an analytical model, which is the actual numerical model in which the assessment is carried out. It might be finite element model, finite differences model, or limit equilibrium model for stability assessment. Next one, please. In terms of the geological and geotechnical model, we start the process with understanding the regional geology using regional geological maps, which are generally available. These are the basis for the TSF site geological model. The site geological model is then refined through field mapping, field investigation, and laboratory testing in a systematic iterative process to determine and verify the conditions of TSF throughout the design life, throughout the lifespan of the facility from planning to closure. Next one. Site seismicity is a very important aspect of TSF performance, and the objective described in our bulletin is to establish design ground motions for seismic response assessment, seismic induced deformations, liquefaction assessment for both the dam body itself and the foundation beneath. Very importantly, we have to establish those for tailings themselves, for upstream and centralized structures, which partly or fully depend on the tailings integrity. The site characterization for site seismicity is described as a process of 3 steps, starting with a seismotectonic assessment, in which we define the regional tectonic settings and conditions, identify seismic sources, and define local seismicity. The next step it's a seismic hazard assessment, which is typically carried out through probabilistic or deterministic analysis. And the last step is the design of the ground motion model, which is then used as an input source for design response spectra and design PGAs for a given facility. The way it's written in our bulletin, we provide very thorough recommendations for characterization of the seismic setting, and we recommend that specific site-specific hazard assessment is performed for most tailings dams, definitely for those who have high or extreme consequence category. We put more emphasis on the probabilistic method, but we recognize the importance of the maximum credible earthquake defined by the deterministic methods, while we recognize that the MCE might be quite frequent event in very highly seismic zones, while in relatively stable regions such as Australia, the design earthquake might not need to be greater than an 84th percentile of MCE, because the MCE doesn't really happen that often. In recognition of very complex process in defining the seismic condition for some sites, we recommend that for very high and extreme consequence DSF, it's appropriate to engage a consensus, or to engage a panel of seismic experts to really get a consensus of the site-specific seismic hazards. Tailings characterization is part of the site characterization, but for its importance, we have devoted one chapter, separate chapter, for it in our bulletin. This chapter is based on the ICOLD Bulletin 181, Tailings Dam Design Technology Update, which is now available, and everyone can purchase it and access it through the ICOLD website. The tailings conditions and parameters are important from two perspectives. One is the structural performance of the dam, and then the impact of the TSF on the environment. The structural performance of the dam, again, is dependent on tailings, especially for in case of upstream or in upstream raised dams. The assessment of TSF impact on the environment includes tailings emissions through dust, seepage, radiation, etc. And it indeed impacts the potential dam breach and the impact onto the downstream area, and how we will talk about it a little bit later on. First step in tailings characterization is the classification, and we follow two aspects, the geotechnical and geochemical aspects, in describing and classifying the tailings. The geotechnical aspects basically follow a conventional geotechnical tests, such as PSDs, particle size distribution, specific gravity, plasticity, while the geochemical aspects follow toxicity, neutral leaching, and acid drainage potential, other chemistry, and other chemical aspects. On the bulletin, or the draft bulletin, follows the classification system introduced in the 181 bulletin, and it separates the tailings into 5 broad categories, which you can see on the table in front of you. Next one. The other very important aspect of tailings characterizations are the geotechnical parameters, which are important for the performance of the structure. And indeed, it is a shear strength, compressibility, permeability, state. By meaning state is the in-situ density, void ratio, moisture content, and other conditions. And those conditions in future loadings. From the dam break perspective and deposition perspective, rheology is a very important aspect of tailings characterization as well. And I believe that it's the last slide, Harvey.
Morning all. Eddie asked me first to outline what comments we received following the issue of our first draft on chapters 5 and 6. We haven't received much for the tailings characterization chapter, but we have received quite a few for the chapter 5, which is site characterization. The comments were mainly on the use of specific terms, which we had to introduce into our bulletin, and maybe the inconsistency of those terms used compared to the terms used in different parts of the world. From that perspective, we have provided further clarity and definitions of the key terms throughout our bulletin, and explained that we can't really satisfy everyone if we are fully aligned with, let's say, the European way of describing models. Some other places around the world, such as Australia, might not like it. So for the bulletin itself, we have defined exactly what we mean by ground model, analytical model, and numerical models, for example. So these were probably the biggest changes in those two chapters.
So there's an opportunity for questions on sections 5 and 6. Tony Bennett.
Is it you, Andy? Look, I understand the question.
The question, sorry, Jiri, the question is not, I couldn't hear the question on online. The sound is not very good.
Oh, I'll try and speak louder. So the two parts under site characterization, I'm wondering to what extent the bulletin addresses climate change and thinking about both the hydrology side.
Sorry, the voice is not clear.
And the second item was related to things like permafrost. So temperature would also be a big. Maybe you can repeat.
Yeah. Annika, have you heard this, the question?
No.
No.
Okay.
It has to be repeated. You can hear someone is talking, but not the words.
All right.
I think the question is does the bulletin consider climate change with respect to both precipitation and rainfall, as well as permafrost, etc. And I think to answer that question, we have we discuss it in the bulletin, but we have not tried to go into, if you like, go into the weeds with discussion on that. We do recognize, and particularly for closure, where these structures are going to be around for a long time, that climate change is an important parameter.
That's the beauty of having Harvey. One is asked question, and Harvey will answer, which is good. Thanks, Harvey. There was a question at the end.
Annika or anyone online, can you hear this?
Yes.
Okay, that was the microphone issue, Annika. Should be better now.
Okay, good. There are some questions in the chat as well.
Okay, we'll get to it. Thank you.
Hello, my name is Leonardo Moreno from Canada and Argentina. My question is if the bulletin is addressing also for coal deposited tailings, where you have tailings and also waste rock, and the characterization for the waste rock.
Yes, the chapter does not specifically addresses the co-disposal of rock or waste rock and tailings. but the means of classification, the classification and characterization processes described in the bulletin would cover that as well.
And I think just to add to that, the co-disposal and those aspects are covered probably better in the previous ICOLD bulletin on tailing technology. So you should reference that bulletin for more information.
I have two questions from the chat. What would be the recommendations from ICOLD on the use of UHS and CMS hazard curves for tailings dam design? In tailings characterization, it's also important to include unsaturated and drying characteristics of tailings for semi-arid and arid environments. So the second one, yes, the drying characteristics of the tailings. It's the impact of the site setting, and it's really broadly covered in the section 5 and 6. The first question about the hazard curves for tailings dam design. I have Paul Redland sitting here, who has done most of the work on the site characterization from the seismicity. So I'll ask him to address that shortly. And the last question I have here, some recommendation for evaluation of strength and stiffness. And it's important for closure. Yeah, we have actually the discussion on strength and stiffness is provided in the appendices for in this bulletin. So one appendix is dedicated to soil behavior that really goes into details of strength and stiffness. And the other appendix is dedicated to contractive behavior in tailings and foundation materials. So both of these are covered there. Paul,
can you hear me?
The seismicity.
Okay, this is Paul Ridland from the US. You know, I guess really on the question regarding the hazard curves for tailings dam design, the approach really is it's recommended to do a site-specific evaluation of the seismic hazard and to, you know, kind of predetermine. And I'm not exactly clear what the question is asking for, but you know, to have like a family of curves or something like that in the bulletin is beyond the scope. So really it's the recommendation is to develop site-specific curves, I guess. And then there was a question on the, did you answer the one on the unsaturated?
Yes.
Okay, sorry.
Thank you.
There is one more question in the chat coming in.
Oh, Andy wants to move on, so we'll get back to
Okay.
you.
Thank you.
Yeah, thanks very much, Jerry. Now, the next section of our talk is covering some of the critical aspects of design. And certainly the design section of the bulletin is the longest section of the bulletin, which is appropriate. The bulletin tries to capture important elements of other subjects, but you know, the technical details is what we focus on. And you know, we cover the broad range of risk-informed design, dam failure modes, design criteria, slope stability, hydrotechnical environment. And you know, the basis of it is understanding how these dams behave, what are potential failure modes, and you just see some illustrations of dam failures, which I'm sure you're all familiar with. But we have to, the underlying thing is to understand the dam failure mechanisms. So we'll move into a talk. Andy Small will lead this portion on risk-informed design and other aspects. Andy?
So good day, colleagues. So risk-informed design, many of you are familiar with it, and you're aware that it goes beyond the traditional standards-based approach. David talked about the consequence classification earlier, fair weather and flood classifications, which are really used to inform the flood designs and the earthquake seismic design. there isn't really a linkage for things like internal erosion, for example, to the consequence classification. So we see the risk-informed design as quite complementary to the standards-based design, and we refer to it as an enhancement. The risk-informed design also has a strong linkage to the observational method, and many people don't understand the observational method. They see the observational method as being synonymous with monitoring the dam. That's not the case. To use the observational method properly, it's necessary to predict and measure the performance. And if the performance isn't suitable, then you implement contingency measures. And that's the piece I often see missing, is that the owners have not actually developed designs for contingency measures. They don't know if those contingency measures can actually be implemented. If they do not have contingency measures and they cannot be implemented, then they are not following the observational method. They're just monitoring. And I think many of you are aware that the observational method doesn't work very well for dams with brittle elements, such as Brumadinho. Next slide. I expect most people on the phone are familiar with Morgenstern's DeMello lecture in 2018, where he introduced this concept of performance-based, risk-informed, safe design. These terms actually have been used in other industries. He just brought them over to our practice. And if you go into his DeMello lecture, you will understand more about what he's describing. We were, with his blessing and with his approval, we distilled his DeMello lecture down to the following points. Identify the failure modes, identify the performance parameters, establish the performance criteria, establish trigger action response plans, monitor and document performance, and take action depending on that performance. Now, it looks very similar to the observational method, and in fact it is. But what the PBRISD process calls for is more significant rigor, a much deeper dive examination on the failure modes when establishing the performance criteria, supported by very robust analyses. The TARPs are a lot more detailed, and so on. So there is a similarity, but there's a higher level of rigor if you want to use this approach. And we're seeing, if we can go back to that for a moment, Harvey, we're seeing this approach being used particularly in Alberta and Canada. And the owners are providing safety statements on their dams based on their performance, and in fact are not necessarily reporting things like factor of safety. They're showing how the dam deformations are performing as expected, and therefore the dam is safe. Next slide. So we're all aware that slope stability is a common cause of TSF failures, and there's been many deaths, lots of contamination, and significant losses to the owner and society. We also need to acknowledge that the potential for slope failure exists in closed and decommissioned TSFs. Brumadinho, for example, was considered closed, but yet it failed. And there's a misperception in the industry that if you can close a facility and get the water off the top, the facility would be safe enough and not threatened by a slope instability. We need to pay close attention to closed facilities as well as operating facilities. Next slide. Jerry talked about the site conditions, and there's a very, very extensive discussion in the bulletin on the site characterization. And that's intended to try to help the practitioner understand what we mean when we say good practice with regard to site conditions. We're going to talk about targets, factors of safety in a moment, but we anchor it to having a very solid understanding of the site conditions. Then going through the different failure modes that could affect the slope stability, conduct a stability analysis and evaluate the results. Next slide. The section that we have in the bulletin is actually entitled Slope Stability Assessment and not Slope Stability Analysis. And the reason for that is because we talk about limit equilibrium as well as nonlinear deformation analyses. You will may have heard Morgenstern's lecture in 2016 in Hong Kong about how he was saying we as an industry need to move away from limit equilibrium analyses and move more into deformation modeling to assess the safety of a dam. That fits with his PBRISD approach, But we all know limit equilibrium analysis is not going to go away. It's still a very important tool, especially for new dams. We spend a lot of time in the bulletin trying to educate people on how to do the limit equilibrium analysis properly. We talk about the challenges with them, the limitations of limit equilibrium analysis, and we spend a lot of time on the conditions when contractive elements are present. And you're going to see several slides on that in a moment from Raphael and Paul. We try to emphasize that limit equilibrium should be used as a screening tool and that it's not perfect. But at the same time, these deformation analyses are not the panacea a lot of people believe it can be. We are aware of several situations where there was garbage in, garbage out. If you still don't understand the materials properly, then what you'll end up with is false results. So neither of them is perfect, but the two can be complementary. Next slide. So this is just a typical cross-section of an upstream constructed tailings dam and the types of things that you would have to consider when doing the slope stability assessment. This is where typically we would have contractive tailings. And I know many people in the world are saying these types of designs shouldn't be undertaken. This is we're moving away from this. But we are aware that there are many, many dams in the world that still look like this. And the material properties is bolded on this slide just to reinforce what Jerry was saying earlier about the characterization and properly understanding all the materials within the tailings dam and the foundation. Next slide. So when undertaking a slope stability assessment, we talk about a number of considerations, such as the consequences of failure, how complex the geology and situation is. And in the site characterization discussion, we talk about how it's important to assume that the site is complex until you do enough investigation to prove otherwise. Time and time again, we run into the situation where sites are being represented by oversimplistic models. If you have dilative tailings and dilative foundation, things are far more simple than contractive conditions. How are the variabilities and uncertainties being addressed? And especially early in the design stages when your site characterization may be limited. Strain incompatibility is a big deal. Morgenstern advised me that at Mount Poly, they did a flak analysis of Mount Poly that showed that the foundation clay actually went past its peak and hit residual before the rock fill shell got anywhere near its peak strength. And a limit equilibrium analysis could not pick that up. The other aspect is how you interact with the observational method. How have you embraced the observational method in your analyses? Next slide. So this is a key piece that people will be looking for. We have established two targets: static conditions, minimum factor safety 1.5, post-liquefaction, minimum factor safety 1.1. Again, many of you are familiar with these types of numbers, but we are aware of many jurisdictions that aren't adopting or have not adopted post-liquefaction. And in fact, they talk about post-earthquake or they talk about earthquake conditions and they mix it up with pseudostatic. And we talk in the bulletin about how that's incorrect. These targets apply to both planned and operating sites as well as closed dams. And like I said earlier, this is anchored to good practices for site characterization, selection of parameters, and so on. Next slide. When doing a slope stability assessment, there's a range of conditions, and we describe those in the bulletin. If you have contractive elements in the dam, we still are asking for a factor safety greater than 1.5, assuming peak strengths if there are contractive elements in the dam. Raphael and Paul are going to talk about the post-liquefaction conditions and how those contractive elements are to be dealt with in a few slides here. And when we're talking about clay foundations, we need to be considering the potential for the clay moving to residual strengths. Next slide. You might be looking for target factors of safety on end of construction, rapid drawdown, and seismic and post-seismic loading. We do not provide those in the bulletin. We talk about it, but that's left to the engineer of record, the RTFE, and review boards to land on specific targets for those conditions because they're very site specific. Next slide. Now, we use the word target minimum throughout the document. What we're trying to do is avoid the situation where one number is cast in stone, we're asking the engineers, RTFEs, accountable executive officers to develop targets that make sense for their project. We're providing these as initial targets, initial screening values, but the EUR should be reflecting on those targets and asking whether they're appropriate for their site and do they handle all of the different things. We're suggesting, for example, the target factor safety may need to be increased for a closure, handle uncertainty, strain incompatibility, and so on. Alternatively, it may be appropriate to decrease the target factors of safety. And we see that in the oil sands in Canada, where they target factor safety 1.3 because of the comprehensiveness of their site characterization and how they have embraced and implemented the observational method. So these numbers should not be cast in stone. We know that's probably what's going to happen, but we try to provide enough information for the practitioner to develop a target that's particular to their site. The next slides then get into more details on adjustments related to contractive tailings. I think the next slide is over to Raphael.
So Raphael Monroy from our UK committee is going to present in what we call Appendix A. And then Paul Ridlin will be talking about Appendix B. Why I'm sharing that with you is because when you see the slides Raphael is presenting, you'll see Paul's name on them. So there was just a confusion there. We're going to get through Appendices A and B first, and then we're going to pause again for questions on this whole slope stability discussion. Okay.
Thank you, Andy. Brief introduction to the appendices in the bulletin. The bulletin contains 2 appendices, and those accompany the section on slope stability. I will be introducing the first one, and that's on shear strength and deformation behavior of soil and tailings. And Paul will be introducing the second one, which is on the stability analysis framework for tailings dams in contractive soils. Now, these 2 appendices were prepared and they were sent to a number of reviewers across the world to get their viewing and comments on the appendices. So they have been reviewed, and I just want to take one of the comments from one of the reviewers, which says, I must say that the appendices provide a very valuable contribution to the clarification of many issues that are important in the assessment of the stability of tailings dams. It is a challenge to try to summarize in a clear way what is in fact a full soil mechanics course in a limited space, but I think that the overall goal has been successfully achieved. It is a complex subject to talk about shear strength and deformation of soils and stability. Tailings dams. The appendices don't get into the detail, but what they give is a fundamental, particularly Appendix A, the fundamental concepts of shear behavior as they relate to tailings. And the reason for including this appendix is because it was felt that there were gaps in the understanding in tailings practice, and that this gap in technical understanding has probably contributed to past failures. This Appendix A tries to present complex mechanics in a level that can be understood with someone with a technical background, but someone that necessarily doesn't have the benefit of having attended a course in advanced soil mechanics, but still highlighting those issues that are important to understand. And these are drain versus undrained shearing, and then dilated versus contractive behavior, and then strain softening behavior against strained hardening behavior, brittle behavior versus ductile behavior. So all these issues are explained in Appendix A to a level that someone would be able to understand the concept without getting into the details. Someone wants to get into details, they can go into the to any textbook on soil mechanics. Thank you. Next slide, please. The appendix also provides additional guidance and comments on CVT-based method of measuring in situ state and soil properties, on the assessment of liquefaction and residual strength of tailings and soils, on the selection of the appropriate shear strength parameters for design and analysis, and how conservative one should be, depending on the uncertainty, and then the pros and cons of using laboratory versus field data. The stress-dependent behavior of materials is highlighted. Partial saturation is briefly mentioned, the same as progressive failure, and strain compatibility between similar materials. These are, the appendix doesn't get into any detail, but mentions, let's say, the subject and highlights the need to understand all these issues if someone is going to be involved in the design of a tailings dam, especially on an upstream tailings dam. Next slide, please. One key point that the appendix tries to highlight is that shearing in soil is accompanied by volume change, and that has very important implication. And that diagram in particular is not in the bulletin, but it's taken from the paper by Casagrande, where it shows that depending on if you shear sand, depending on the density, you will have an increasing volume or a decreasing volume, and you also have peak strength, or you go to an ultimate strength. Next slide, please. Now that diagram is in the bulletin. What it tries to explain is the difference between drain and undrained shearing. And at the same time, what it shows in particular, that diagram with the undrained shearing, is that if you have the type of response that you could expect if the material was to contract and generate positive pore water pressure. So if you had a drain strength path, then you would go up to the, in this case, to a critical state strength. You have a high strength. Whether if you have undrained loading, you will have a much lower strength. And that in particular would be what you will get from a triaxial test on a sample. Next slide, please. The other important topic that the appendix highlights is the difference between dilative and contractive behavior, and the importance of density in determining strengths, not only the stress that is acting, say, on an element of tailings in the tailings dam, but also the state at which that sample is in relation with the critical state line. Whether it is a loose sample, and during shearing it will generate negative pore water pressures and it will have a reduced strength, or it would be dilative and it will generate negative pore water pressures and it will have a higher strength. And if these things are not taken into consideration, then one can sort of misrepresent the strength of the material in the field. Next slide, please. And leading from that, and in particular when it comes to undrained loading, it is also important to realize that there is some materials can show the brittleness as one shears them in the drain manner. You could also have a drained, but probably of more interest, particularly when it comes to upstream tailings dams, is whether that material, when you load it in an undrained manner, it can lose strength or not. Would you reach a peak, and then after that peak, would you end up in a residual post-peak critical state strength or not? And what the bulletin has done is looking and recognizing that it is, and depending on how you test the sample and what type of test you do, you might get different results. But still, some materials will generally show little brittleness. That's what is shown in the diagram on the left, the green zone. Some materials will show some slight brittleness, some loss of strength after peak, and some materials will be highly brittle. Bishop defined brittleness index as the difference between the peak and residual divided by the peak strength. And Robertson suggested that brittleness index is renamed as strength loss index to recognize the use of that parameter to measure the magnitude of strength softening. And this is used as a basis for then having a number of cases that one can consider when assessing the stability of a tailings dam, and that leads on to Appendix B. I think that will be the last slide. Can we go to the next slide? Yes, that will be the. Thank you.
And Paul Ridland from the United States is going to present the section on Appendix B. Paul, turn it over to you.
Okay, sure. So as Raphael and Andy have talked about, the two appendices A and B are tied to the stability analysis sections. So in the stability analysis section of the bulletin provides a general discussion and overall approach to analyzing the slope stability. And then Appendix A provides these foundational concepts that have been unfortunately misunderstood and misapplied in tailings dam design and are still being misapplied in tailings dam design. We were at Tailings and Mine Waste Conference in Alberta last week, and there was a case history that was presented that was a demonstration that there still is a lot of misunderstanding and misapplication in tailings dam design around the world. So what we've tried to do is, again, as Raphael described, provide a general kind of a primer, a description of shear strength and deformation behavior that's written to a person with a basic understanding of the technical concepts, perhaps a civil engineer or another engineering background, so that you have some understanding of stress strain behavior and mechanics and materials, but maybe have not had a full appreciation of the higher level soil mechanics. And then Appendix B tries to take that that foundational understanding of soil mechanics principles and helps apply a logical framework to solve some of the more difficult problems. It is very important to recognize that different materials behave differently, and they behave differently under different loading conditions or environmental conditions. So the behavior that may occur early on in the dam development could be very much different than the behavior at a later time. And this also builds and provides a logical framework for dealing with the concept of target minima that Andy talked about, so that if you can design with a very conservative approach, meet the minimum standards in somewhat of a standards-based approach, then there's no problem. But if, as many of the challenges are very complex, and there may be times that it's difficult to meet those targets, there needs to be a logical basis where engineers can walk through a process and understand kind of the situation that they're dealing with and apply these principles correctly. So this Appendix B provides this logical framework to select the factors of safety when the minimum targets cannot be met. It also addresses the analysis techniques that can be used, and it helps to make the decision of when and how to apply nonlinear deformation analysis when that's appropriate. We do want to emphasize that for new facilities, we really don't want to see contractive materials placed within the structural zones, if at all possible. And so in some cases, it is not possible for various reasons to avoid placing contractive materials in the structural design or in the structural zones. And in those cases, we have to consider the potential for undrained shearing. However, we should never knowingly place brittle materials within the structural zones of a dam. It's just too dangerous. We can't predict, we can't control, we can't monitor brittle behavior. And those applications need to be avoided for new facilities. But for existing facilities, we have to recognize that we have a large portfolio around the world of tailings dams that have been built with contracted materials and potentially brittle materials in the embankments or perhaps in the foundations, similar to what happened at Mount Poly. And so we we need to recognize that when we're dealing with these loaded guns, so to speak, we have to recognize the downstream consequences, and that will also influence our decision making. And it also really tries to emphasize the importance of this post-liquefied condition as the primary design element, where I think in past design processes, people have focused on peak strengths and drain strengths, and then they do an after check kind of as an afterthought of what the post-liquefied condition would be. And so what we're saying is when you have contracted materials, you need to first look at the post-liquefied or the large strain behavior and see your ultimate state and make sure that your dam will be stable under those conditions. And then there may be some optimization that could be done through looking at peak strengths. Go ahead and go to the next slide, Harvey. So Raphael just introduced the chart that we presented that divides behavior up into brittle or highly brittle, non-brittle, and slightly brittle, or a transitional material. So, you know, I guess we've tried, there is a gap, a little bit of increase in understanding and characterization of brittle behavior. A lot of attention is being given right now in research and in writing and in education on recognizing brittle modes of failure. Two things that are important are the total magnitude of strength reduction post-peak, but then the other aspect is the rate of strain. And the strain aspect, I just want to comment on, is very delicate and very complicated, and is probably oversimplified in this figure here. But what we're trying to do is help to recognize these different behavior types. And so we developed a flow chart, which is on the right, that helps walk through the different cases where we would ask the questions of, first, are contractive soils present? And then if they are present, are they potentially strain softening? So if they're strain hardening, or perhaps only just a slight amount of softening, we would describe that as in our framework of case one, and there are a general approach as how to analyze that. And then if we do have strain softening materials, we ask ourselves, to what degree does strength loss occur post-peak? And if it's greater than 20%, then it basically falls within the yellow zone or the red zone. And so if it's greater than 20%, but less than 40% of total strength loss post-peak, we describe it as case two. And case two should not be misunderstood as being straightforward and safe and nothing to worry about. It may actually be one of the more complicated frameworks, because how much ultimate strength occurs and the level of strain that it takes to get there. And whenever you have strain compatibility, when you have isolated thin zones, we need to be careful that even though the overall facility may only strain a relatively small amount, there could be high degrees of strain in these concentrated elements. And so we need to understand again what that ultimate state is. And then when we get in kind of the worst case scenario, it's when we have soils that are deemed as highly brittle. And we've adopted the recommendations of Dr. Robertson that highly brittle soils, which are those that are most prone to what's known as static liquefaction. And I just want to comment that the red lines on that chart were stress strain curves developed from the Feijoa failure in the investigation. So those demonstrate the type of brittle response that occurred that led to the Feijoa failure. And so when we're dealing with brittle soils, we first want to take a look at that post liquefaction or the residual strength condition. And if we do have a factor of safety greater than 1.1, if we're assuming an appropriately conservative strength and we have a factor of safety of greater than 1.1 for that residual strength condition, and we've adequately characterized the material, then by and large, static liquefaction is not really possible, because the stress level will be held to a point where it can never get up to the peak, and it will be statically determinate under all loading conditions. However, if the factor of safety is less than 1.1, and especially the lower that factor of safety gets, the higher your risk is and the greater potential for flow failure. And so if we have very high downstream consequence, we need to recognize that extreme measures will need to be taken. So if there's a highly brittle material in a dam that has a high number of people in the downstream flood zone, and this is what's happening, what many people are dealing with in Brazil right now as they're trying to go through their old facilities and assess what their risks are. There are several cases where this condition is being met, and so some type of urgent activity must be done, whether it means removing people from the hazard zone, constructing some type of retention facility until the tailings dam can be stabilized, or stabilizing those through buttressing or other means, and perhaps even ultimate removal of the tailings dams if that is possible. Those are the types of outcomes. So, we feel like this is a very important, it still can be a loaded gun in the hands of the wrong person. So we have to be very careful that we understand all the principles in Appendix A. We have to be sure that we are recognizing the degree of uncertainty in our characterization, trying to minimize that to the degree possible, choosing appropriately conservative parameters, and then using appropriate analysis techniques. And then I do want to I'll just comment quickly.
Okay, can you hear me? Yes, thanks, Andy. Yeah, we did get some comments, as mentioned earlier. We did, in Raphael, in the pre-recorded section, we sent this out to several experts, recognized experts around the world, and got some feedback during the development of the draft, some great input that we got. And then in the round to the national committees, had several comments. The most extensive came from Dr. David Reed in Australia, and he did quite a bit of work, and we made some very specific detailed changes, all to the better, and we appreciate his contributions. Nothing really of substance that was changed from this version, other than just details in terms of how we handled things. There are a couple of comments throughout the appendix. I just want to note that one of the things I learned in this process was the many different approaches around the world. Jerry alluded to earlier about the Europeans have a very specific approach, a limit state approach. There are different types of terminology that are used for the same types of phenomena. And that's been probably the hardest thing to resolve. I know some people will continue to object about certain terminology, but we tried to handle it with the right type of due consideration. And then any questions from the audience? I know there's some in the chat. I will apologize for 2 references to loaded guns in my presentation. Being an American, unfortunately, that's built into our psyche. Oh, one other comment is we did, the numbering is off. So Appendix A is now Appendix B, Appendix B is now Appendix C. In the latest version, Appendix A is the reference appendix. Go ahead.
Yes, once again, Elias Batista from Mozambique, working for mining company there. Elias from Mozambique, I'm working for a mining company in Mozambique. I have 2 points to ask. There is a new trends in the industry now. The first one is the remining or reprocessing of tailings dams and the use of tailings in construction industry and sands and reuse for putting the new in the process. For example, the coal with high content, they are now using for reprocessing. And the second question is, there is a open pit disposals now as an option for tailings. And this is also a new, say more safer way of dispose tailings, and is an alternative now in Mozambique, for example, the use of these, but the most guidelines are not highlighted or taking this into account. If we talk in the broad perspective, as talking about TSF as tailings storage facilities, we will include the open pit disposals, but we are more focused on the tailing type of dams and other. I don't know if this was addressed on somehow in these new bulletins, or thank you.
Thank you, Mr. Bautista. I would say that indirectly, both subjects are addressed. And I guess, first of all, Annika or anyone else online, were you able to hear the question or the comment clearly?
Yeah, and I agree. It's obviously, if you can put an open pit and it's appropriate, it's a lot safer. And certainly that option is discussed more in the Tailing Technology Bulletin.
Yeah, so yeah, the technology bulletin addresses kind of specific and emerging specific applications and emerging trends. All the principles that are discussed are certainly applicable to remining, you know, with an open pit disposal. For the most part, there's limited downstream consequence because it's a contained environment, and so those considerations in effect go away because of it's really more of an environmental type of contamination that the process would be followed, which again, everything that's in the bulletin sets a general framework. We're not addressing specific applications. We're trying to develop an overall framework that could be applied to every type of problem. So we feel like it's adequately addressed. Comments from the chat. One of them is, I'll just read it: for post-liquefaction limit equilibrium analyses, the determination of liquefied strength is challenging depending on uncertainties and data available. What percentile of strength should be used for a factor safety greater than 1.1? Should we use the lower bound value of estimated liquefied strength for the factor safety of 1.1 criterion? Excellent question. You know, a significant amount of judgment is required in every situation in selection of strengths, and it really depends on the thoroughness that you have been able to characterize, the number of or the degree of uncertainty that's associated with that particular element that you're characterizing. So I don't think that there's really a hard value that could be used to say this is what should be used. You know, certainly if you could start with an absolute lower bound that is reasonably selected based on your knowledge, which, you know, our knowledge is never quite thorough enough with complex behaviors. But if we could start with a lower bound and achieve a factor safety of 1.1, that's ideal. If you can't achieve that with an absolute lower bound, then, you know, a risk-informed decision-making process to go through and assess your degree of knowledge and how much likelihood of an excursion outside of whatever value you select would be the approach to take. And again, really that logical, well-documented, well thought through process is the overall approach that we're trying to recommend. And then there was a question, saline soils are potentially brittle soils. Should they be not used in structural critical zones, or a limited content of soluble salts could be available, could be acceptable, sorry. So again, a very specific example that really is very applicable from the Brumigino, the Feijoa failure, because those were in essence degrees of salts probably that had formed bonding that was ultimately broken. So if there is any mechanism whatsoever that would lead to a brittle failure, then the principles described in Appendix B and C would be completely relevant. So if there's a salt that creates a brittle structure that could be lost with saturation or through deformation or whatever mechanism, then this approach is definitely applicable. So again, we don't think that the mechanism is important. Go ahead. There was another question.
Malcolm Barker, GHD in Brisbane. Oh, you want me to stand? Oh, goodness me.
Yeah, sure.
Come on, Jerry. Yeah, it's just a simple question. With your previous answer, when you're relating your percentile strength or whatever else, you talk about risk, but are we actually talking about factors of safety going into the probability of failure, as opposed to a risk-informed, where you're not actually getting to a probability of failure in terms of applying to a risk analysis? I don't know whether you deal with that at all.
Well, so we aren't directly, you're correct. We're not approaching this from a probability of failure, but that is an approach that could be used. So I guess whichever approach that you would apply in terms of a specific analysis and in the decision-making process, you know, there are multiple approaches that could be taken. What we've tried to do is really just produce a framework, an logical framework, so that, and it is somewhat deterministic based or standards-based approach based on these factors of safety, to really just place yourself, where are you in this spectrum or this continuum of maybe fully acceptable to borderline to extremely unacceptable. And then once you've placed yourself in one of those categories, so to speak, then you would develop a specific solution and approach that would be appropriate to that particular condition or a particular problem. It's very difficult to create specific approaches for the wide range of problems. What we've tried to do is just provide the framework. Does that make sense?
So we have about 20 minutes left of presentation content, and about 25 minutes left in our allocated time. So I'm going to hit play again, and we'll run this through to the end and hold all other questions to the end of the workshop.
On the application of seismic design criteria. So we're kind of now jumping back to the main bulletin, walking through the design section. We've talked about other aspects of design. The seismic design criteria generally follow the minimum criteria that are recommended in the global standard. We've added some footnotes. I think one of the things that the global standard did was really recognize that a one-size-fits-all solution is never really the right approach, that there needs to be a combination of probabilistic and deterministic analyses for your seismic characterization. And the seismic criteria that are in the global standard are primarily based on probabilistic analysis, but there are allowances for deterministic or MCE conditions in certain cases, but the standard does not really provide a lot of guidance on how to make that decision. So we've tried to embellish that a bit. We have these footnotes here that really, again, reemphasize the importance of considering the seismic setting on selecting the design earthquake based on both a probabilistic and a deterministic or scenario-based approach. And then also referring to a risk-informed decision-making process to try to select design criteria to reduce risk to as low as reasonably possible. We also want to, I just want to reemphasize what Jerry mentioned earlier in the site characterization aspect, is that it's not that in every case you'll need to have a panel of seismic experts, but oftentimes when you have a large discrepancy between an MCE and a 10,000 year earthquake, for example, kind of historically, I think a lot of people have felt that an MCE always is a very rare event that doesn't occur very frequently. But along the plate margins, the MCE may actually have a relatively high recurrence interval. And so those are the cases really where there may be some extra expertise that needs to be brought in to make the selection of that design criterion. And that is included in this bulletin that provides a bit of a basis for practitioners to resolve what can sometimes be a very difficult decision that needs to be made.
Briefly talk about the hydrotechnical design section in our guideline, because TSFs are as much about water as they are about tailings, and so water is a vital part of it. We typically would have a minimum water pond to allow settling of fines and potentially geochemical attenuation if that's a factor. We would then want to have some temporary storage of normal seasonal flows. There might be some requirement for ice storage in cold climates, and we might need to have an environmental design flood if the water quality is unsuitable for release under certain circumstances. And then obviously we have to consider the design flood that would be potentially determined by the consequence category that I've been talking about earlier. Next slide, Harvey. Not coming through. This diagram really shows these water levels I'm talking about. So our normal operating water level would have a bit of a float on it for our seasonal conditions to determine a maximum operating level. And then above that, we would want to have an environmental design flood storage capacity, in which case we could spill from the dam, or some dams we are designing to retain the inflow design flood. And then there'd be a wave run up and freeboard on top of that. Next slide. Just to pick up on a few pretty important points on this. Operating levels should be based on a detailed water balance, and this is very important. I think understanding the water balance in the TSF is a vital part of safety. ICOLD recommend an emergency spillway is provided, even if you're storing floods and don't expect to have a spill. I think we have to allow for the unexpected, and if possible, we should have some sort of provision if the floods reach a higher level than we expect. What happens to them? It's much better to have a spillway than to have the dam overtopped. If we do consider this environmental design flood, we really have to consider that the water that comes in over that flood event can be removed over a certain time. We've got to understand how it's going to be removed. Sort of things we'd have to consider about in our environmental design flood would be all these listed here: water quality, etc., and the downstream receiving environment, and even public perception. So there's quite a lot of factors to consider. But typically, we're looking at long duration events. They could be weeks or months. So in some parts in Australia, for example, we consider in the tropical areas wet seasons of 2 to 3 months for the inflow of water for these environmental design flood considerations. Next slide, please. Obviously, we need to consider the effects on the receiving water. I'm moving on to now environmental design. Obviously, water is a very important part of it, and the receiving water quality, potential for dust emissions, and the effect of flora and fauna are very major environmental issues we need to consider. We're really looking for our long-term geochemical and ecological stability for closure. And to be able to design for this and consider it, we really need a very good understanding of the chemical and geochemical characterization of the tailings and the water that we're using in the dam. And particularly important in a lot of the design decisions is the transmission of contaminants in groundwater. We need to understand that really well. Speaking of that side of it, the seepage that comes out of the dam has to be understood, and when I say allowable seepage, it's really what seepage rates are possible without affecting the environment. And if we can't control those by normal methods from the tailings themselves, we might have to look at liners and other seepage prevention methods. So this is becoming a more important aspect of contaminants in the groundwater, and it's a design issue that we're going to be facing more in the future. Monitoring programs are very vital for tailings dams, and also air quality is becoming more important as well. Thank you. I think that might be, oh no. So I guess if we do find we have environmental issues, there are various ways we could consider mitigating them or preventing them from occurring in the first place. And examples of this would be not using cyanide, having a different process to remove some of the concerns, potentially processing tailings to remove the properties that are not desirable for the environment, like sulfides, adding minerals or chemicals to neutralize sulfide reactions during the tailings dam operation, or potentially compaction of saturated tailings to prevent oxidization of potential acid-forming materials.
Risk management is really what the whole process is all about. The whole bulletin, at the end of the day, we're managing risks of our tailing facilities. And the underlying part of that is to understand these potential failure mechanisms. And you've heard in these talks right now that it's never that simple. We have different materials and different types of mechanisms that can be happening. And that's a key fundamental basis for risk assessments. And there's many risk assessment tools, semi-qualitative and qualitative, quantitative rather, methods. And we don't get into the details of those. There's lots of guidance on that. But the key element is identifying what could happen and what are preventative controls. What are things you can do to prevent that from happening? And they may vary anywhere from having extra rigor in your review and analysis and monitoring to actually constructing some aspects. But you want to be looking at your preventative controls, and for example, piezometers, measuring deformations, etc., can be your preventative controls so that you do have warning of what might happen. And it's a iterative process with respect to, you've heard the terms critical controls and TARPs, trigger action response plans. And they, you go down below here, you have normal conditions where your piezometers or inclinometers or everything is normal and it's behaving as you expect. And then you start moving into a condition where, for example, piezometers may be increasing and you may be trying to figure out why they're increasing. And obviously, if you don't understand why they're increasing, then you have to dig into why. And you start moving into a case where they're still increasing, but you really do need to start taking actions such as building a buttress, moving the pond, different actions. So, and these are basically typically covered in the OMS manual, but there's a transition between the OMS manual and the Emergency Preparedness and Response Plan. And certainly if you have a facility where you're starting to get into, the phase 2 of the yellow area where you have, potentially the dam may be, for example, moving, and you're still haven't arrested the deformation, then the emergency response team should be notified and start working on it. But the emergency response plan really kicks in when you get into the potential emergency situation, and I'll cover that in the next slide. And the International Council of Mining and Metals has a, you probably can't read it, but this flow chart for deciding what is a critical control. I mean, you'll often see people putting in piezometers that really aren't critical controls. A piezometer in a rock-fill dam is probably not a critical control. It's a nice to have. So it's important to be monitoring the right things, and the bulletin describes those components. Now and it was covered a bit earlier, the dam breach assessment. And the Canadian Dam Association has a very good bulletin on dam breach assessment. But the underlying uncertainty with dam breach assessments is understanding, well, I guess it's backing up a bit with David mentioned, you have water eroded tailings and liquefied tailings. And I think the understanding of what's eroded by water and what's eroded or what is caused by liquefaction is very just poorly understood. For example, water eroded tailings that to me it's probably the biggest driver of the dam breach, with the Brazilian failures being the exception. But, for example, Mount Poly and Ajika, Mount Poly, which is a hard rock tailings, Ajika in Hungary, which was a altered rock tailings, the total volume of release was of tailings was about equivalent to the volume of water released. And it indicates that, the water is a major driver in understanding how the tailings may behave, and that gets into, what is the void ratio of the tailings, what is the liquidity index of the tailings, how susceptible is it to flow, how brittle is it. And so this uncertainty as to the quantity of tailings release is probably the biggest uncertainty with the hydraulic models. There's been tremendous progress in hydraulic models and being able to model Newtonian and non-Newtonian flows. And so the science of modeling is very well advanced and continues to advance tremendously. But it's this link with how much of the tailings is going to liquefy after the water has left the ship. I mentioned emergency response plan, the link back there. But it's important that and this is embedded in the bulletin, that the emergency response team and the operational team, they have to understand, this is a potential failure mode. And I use the example of, let's just take an example of water. And it's raining and raining, and we can quite relate to that today in Vancouver. Where the province of British Columbia is a state of emergency. We've had washouts of major highways, railway, flooding of towns, and devastation of livestock, etc. So rain happens, and you can get unusual events. And if you're on a tailings facility and it just keeps raining, you want to have thought out the scenarios before. Can you excavate an emergency spillway in some abutment or an area of the dam that is less susceptible? Can you raise the dam quickly? What can you do? So it's a key element, not just that the emergency preparedness response plan has to be linked right back into the operations and into the failure modes and the arresting and management of failure modes. Now, the next set of slides is on construction and operations. And Duncan, are you there? I can turn it over to you.
Thank you, Harvey. Yes, I'm here. This section on construction is a comparatively short section, but it focuses not on how to construct a tailings dam, but more on the controls that need to be in place during construction. And the essence of it is that construction management and supervision, QA/QC, have got to ensure that the design intent is met. And the second important point here is that the engineer of record is ultimately responsible for the design and documentation specifications and the safe operation of that tailings dam. So it's extremely important that he has to be part of the design team or the construction team and have an ongoing involvement during construction. Next slide, please, Harvey. Sorry, yeah, thanks. Yeah, the EOR has to sign off on the foundation on all of the critical phases during construction. And I think it's important here to also note that construction of a tailings dam, unlike a water dam, is an ongoing process throughout, or basically throughout the life of the dam. But the EOR has to sign off on the foundations, the materials used, the construction methods used, and he has to be aware of changes to design during the course of construction. And bearing in mind that the construction of a tailings dam can go on for decades, there's bound to be changes of, first of all, the tailings itself, as different parts of the ore body might be processed. There's going to be changes in ownership of the mine. There's going to be changes in regulatory authorities or in regulations. All sorts of changes, and the EOR has to be conscious of that and to keep updated with that. Next slide, please, Harvey. Documentation, incredibly important. As constructed records are absolutely necessary. Construction reports are necessary, and we need a data management system for all construction records. All too often, you will get a query about what happened 10 years ago and nobody can find any record of it. It's extremely important that a data management system is in place during the life of a tailings dam. Next slide, please, Harley. Let's move on to operation here. Again, it has to be in accordance with approved procedures. It has to be documented in the OMS manual, and it's got to be overseen by competent people. And again, once again, it has to meet the design intent, and obviously also has to comply with environmental requirements that might be in place in whatever jurisdiction it is. Next slide, Harvey. During, essential parts of the operation is that you have to control the distribution of tailings to meet both spatial and consolidation requirements of tailings. You've got to maintain your pool control properly. That's pool level, pool position, freeboard. If, for example, if you've got a pumped decanting system, you need to make sure you've got enough water under your pumps. You've got to make sure that your beach lengths are adequate. And you need to optimize recycling of water. But at the same time, we also need to try and control dust generation, and that's normally done by rotational deposition on the tailings dam just to keep the beach damp. We also have to ensure during operation separation of contact and non-contact water. You don't want clean and dirty water getting mixed up. Thanks, Harvey. Yeah, I think that's the end of it, is it? All right. The OMS manual, this is an incredibly important document. It's got to be completed prior to commissioning of the tailings dam, and it needs to be updated regularly. It's a living document. It's, as a minimum, it's got to include tailings characteristics. It's got to have a description of the tailings dam itself. It's got to define roles and responsibilities. It's got to give you a deposition plan, a deposition method, and a schedule for deposition. It's got to list the key design criteria. And there are a whole lot of other aspects. I think they're on the next slide, Harvey. It's got to detail the monitoring and surveillance requirements. It's got to have a risk register, maintenance requirements, for example, pumps, pipes, spigot points, etc. It's got to list your critical controls and your TARPs as well. Then obviously I've got maintenance requirements twice there, but training requirements. It's very important that your operational staff are properly trained to do the job, and that talks to the earlier statement I made about the competence of the operating staff. And finally, there's got to be a summary of the emergency preparedness plan in the OMS document.
So that concludes the presentation. We're a couple of minutes to the hour. I think we're going to wrap it up with some closing remarks here. I'd like to thank Oyvind here for his tech support. He's our committee member from Norway. Nice country, I hear. Just like that. We didn't acknowledge David Brett. So when section 7 came along, we didn't step forward and indicate that David Brett from our ICOLD group was the presenter of that. You would have caught his Australian accent, but he did section 7. I'd like to ask that our committee members stand, all of our Tailings Committee members for a moment. So Oyvind, Joachim, Violetta as an observer. So on the Bulletin Committee was Paul, Joachim, and Jerry. And then Heli from Finland, Oyvind from Norway. Now Violetta here is an observer from Canada, but she's one of the principal authors on the CDA dam breach guidance. So if you have questions on dam breach, direct them to Violetta. On that note, I'm going to bring the workshop to a close. I thank you for your attention, and to those online, I thank you for your attention. I was communicating with some of you. It's like 2 in the morning for some of the folks that are there, and we appreciate your dedication and enthusiasm towards this important subject. So thank you very much.